All right, how's it going, guys? Mr. Fortin here. I know some of you still working on this. I see you up there. See the names there. Let me anonymize so I don't get this here. But I know you can do it. You can work through it. But sometimes, guys, let's face it, sometimes it's nice to hear kind of how a teacher would present it or a teacher would go through things. So I'm picking up on slide 11 of today's assignment, day 2. Reference angles, right? If we're going to talk about an opposite over adjacent ratio, right? We're going to talk about a ratio here. We got to know what angle being talked about here. So here's our reference angle. In any reference angle, any angle here within a right triangle would have its own opposite over adjacent ratio. It's unique to that particular angle. That's pretty cool here. So here we got an 18-degree reference angle, and its opposite over adjacent ratio is 5 to 15. Okay, or if we simplify that, it's 1 to 3, right? Here. This here, right? Whatever this is here, height times by 3 would bring you to this here, the adjacent side of this right triangle here. This opposite side here is 1/3 the size of the adjacent side. So if we just multiply by 3, we get whatever this is here. This question here is asking us, a giant's 10.3 feet tall. How far is she from the end of the string when her head touches the string here? Well, if they're 10.3 tall, so if they're 5 feet tall, they're 15 feet away. If they're 10.3, it's going to be more than twice that. It's going to be more than 30. So the question is, can we get more precise with that? And right, we can set up a ratio if we want to treat this more like a similarity problem here. Then you can do it this way, right? 5 over 15 is going to equal, well, we don't care about 5 for height, right? Our height's in the numerator here, height to ground length. We want to know height here, 10.3 to ground length. That's what we're going to find out here is x, right? We can set this up. This is a proportion, cross multiply, right? 10.3 times 15 is 150 something. Divide by 5 and we solve for x, get our answer there. Or what can we do? Well, we can just take that 10.3 thing. Let me estimate it out here. 10.3 is about twice the height, so maybe it's right here. 10.3, and remind ourselves that this ratio is going to be in a 1 to 3 ratio here. So if our height is 10.3 feet, shouldn't I just be able to multiply that by 3 to figure out, well, how far along they are? Sure, I can, right? Because these two triangles are similar in one another. We got an 18-degree reference angle, and we have a 90-degree angle there, a 90-degree angle there. So our green triangle here is similar to this triangle up front here by AA. Okay, 10.3 feet, multiply by 3, and that's going to tell us our answer. That's how we're going to do it. We're going to do a lot of multiplying here in our upcoming unit on trigonometry here. So I do 10.3 times by 3, and I get my answer. I get 30.9 feet. Okay, and I don't even need to explain that, right? 30.9 feet. And when I'm double checking it, I'm just going to multiply that quickly in my head by 3 and get the answer. So hopefully you got it. You can set it up as use similarity to get there, or you just realize that this is in a 1 to 3 ratio. Multiple by 3, it's going to tell you the 3 parts 1. You already have the 1 parts 1, 3 parts 1 there. All right, question number 12. Let's keep going. Show your thinking and work in the text box and in the text box here. In a right triangle, the opposite adjacent ratio is 20 over 60 is the reference angle, 18 degrees. How do you know? So you don't have enough space for this, I don't think. Do you? Is there 60 here? Let's check it out here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's a lot of work here, right? A lot of work here. But I think ultimately the point of this is, well, 20 over 60, that's just 1 over 3, right? 1 over 3 here. And so maybe instead of 20 over 60, maybe we do 2 over 6 to sort of demonstrate this. Well, 2 over 6, okay, 2 over 6 in a right triangle here. This is our reference angle here. That would mean that 1, 2, 3, 4, 5, 6. If my slope angle is that, okay, it's a little bit smaller than what it wants to be. Maybe I'll do, yeah, let's just do 2 over 6. Let's do it here. Right angle right here. This opposite, the opposite to adjacent ratio here, okay, here's my theta. Here's my reference angle. Opposite of that, I got length 2, and I have width of 6 here, okay? So instead of 20 over 60, that would be the same as 2 over 6, or 1 over 3 here. So the question is the reference angle 18 degrees? And the answer is yes, right? The answer is yes, because here, if we're in a 2 to 6 ratio here, based on the one that we had here, okay, this triangle here is technically similar, right? Similar to the triangle that you had on the original slide. This one here, 18-degree angle is in a 5 to 15 ratio, okay? And 18 degrees here, a right angle here, and then 5 to 15. That's in a 1 to 3 ratio right here. Right angle in between here. So if we wanted to make the argument that this angle had to be 18 degrees, it technically has to be by SAS inequality, right? Not SAS, SAS similarity here, because the original triangle that we had with 18 degrees, let's put a question mark down here, 18 degrees. Well, we know from the other slide that if we have a 15, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, I got to stop it here. I'm going up 1, 2, 3, 4, 5. Bring it down here. We were given this, that this was 18 degrees, and then this is 5 over 15, okay, and we had a right angle. Well, this is going to make the SAS inequality theorem, SAS similarity theorem true, because, check this out, maybe change colors right here, the right angle, okay? Well, do we know this is an 18-degree angle yet? If we have a 20 over 60, right? I'll pretend it's 20 over 60, just scale down by 10s. Maybe I'll put that there, make it 20 over 60, scale down, divided by 10, so we scaled it down. But anyways, do we know that it has to be 18 degrees? Well, we have a right angle there in our slope triangle, right? And we have a 20 to 60 ratio. And check it out here. This is going to be similar. It's because right angles are congruent to one another, right? Right angles are congruent to one another. So we have a pair of angles that are congruent to one another in two different triangles, and their sides, including those, are in proportion with one another, okay? In proportion with one another. So that's how I would justify. As a math teacher, I would love to see that if you justified it that way, but that's how I would justify it. 5 over 15 is the same as 20 over 60 because they both would simplify down to 1 over 3, right? To 1 over 3 here. Okay, so what that proves us is that this certainly has to be 18 degrees. Okay, so I might write this out as kind of, and you'll see this later maybe to share, so, whoa, what math teacher wrote that one, this one here. I'm going to go yes. Okay, yes. How do you know? Okay, well, by the SAS similarity theorem, a triangle with a right triangle with legs of 20 and 60 would be, so that's the I'll say the thing. I'll say the similarity thing afterwards here. A right triangle with legs 20 60 would be in proportion with a right triangle, or it would be similar. I might put that. It would be similar to a right triangle. Right triangle with legs of that. Yeah, right triangle with legs of 5 and 15. Okay, I know this because 20 over 60 equals 5 over 15. So the sides that are side lengths, maybe you say, so the side lengths that are including the two, and then in parentheses, congruent right angles are in proportion. Okay, therefore we've satisfied, therefore the two triangles are similar by SAS similarity. And since from previous slides, we know that a right triangle with a 5 over 15 opposite to adjacent ratio has an 18-degree angle. And we know that any similar triangles must have congruent corresponding angles. Man, lots of writing in geometry, lots of words, corresponding angles. We would deduce that a right triangle with legs legs of 20 and 60 must also have an 18-degree angle opposite of the side length 20. Okay, do I expect you to write that much? No, not really. I don't know if you see what I type in and send out. I don't think you do actually here. Okay, hopefully that makes sense, but that would be my official math teacher kind of justification for that here. And a right triangle of opposite adjacent ratios 20 over 60 as a reference angle 18 degrees. Well, yeah, it is here. 20 over 60, that's the same as 5 over 15. And you have it included right, because they're right triangles, the included angles are congruent to one another. So the two triangles are similar through Sas similarity, and corresponding angles of similar triangles are congruent to one another. So that 18-degree angle that's opposite the 5 in the one we had before is going to be 18 degrees in this side. That's 20 in this one now here. Okay, justified. We're good to go. So whenever we have a right triangle whose legs are in a 1-to-3 ratio, we're going to know we have an 18-degree reference angle there. Right, opposite the smaller leg, right? The smaller leg here. All right, next up here. Wow, that was a lot. I wasn't expecting it to be such a hard problem on there that you guys had here. Jose Manuel loves finding shortcuts. He asked a group, what if the string were at a different angle? Can I still use the same ratio to find the opposite and adjacent sides? No, you can't use the same ratio because 18 degrees is different than another thing, okay? Because if you had the same ratio, then that original triangle would be similar to the new triangle you have here. And it's not, because it would have a different angle here, okay? So the answer, I think, would say no, right? If I have more than, like, say that this is like, what is this, like a 40-degree angle, then this, right, this here, okay, way bigger. This is definitely not a 1-to-2 ratio, or sorry, 1-to-3 ratio or something like that here. If the swing were at a different angle, then the opposite to adjacent ratio would not be 1/3, right? Not be the same as the opposite over adjacent ratio of the 18-degree reference angle. Okay? If the ratio, as we discussed in the previous slides, right? If the ratio were the same in the new triangle, then the new triangle would have to be similar to the original triangle, right? With the 18-degree angle and 5-to-15 ratio. But this is impossible, since that would mean the reference angle would have to be 18 degrees. Because corresponding angles of similar triangles are congruent to one another. Sort of like an indirect proof that I just wrote there. Okay, so therefore, if a triangle has a reference angle, if the string were at a different angle, if the string were at a different angle, then the op over adjacent ratio must be different than 5/15. Okay, because the new triangle is definitely not similar to the 5/15 ratio right triangle, because the angle changed after all. That was the premise of this problem here, okay? Kind of wordy. Hopefully you follow my logic there, right? And more of the story is got to type something up and kind of get something like that and turn it in and become good to go. Okay, 14 here. Let's check this one out. Hey, I got a couple questions about this one. So Yancey wanted to know the opposite over adjacent ratio that goes with a kite string that touches the ground at an 11-degree angle. The reference angle measures 11 degrees. We actually dealt with this, I think, on Wednesday's class, the 11-degree relationship. If I have a reference angle here, here's my theta, then what's the opposite over adjacent ratio for an 11-degree angle? Let's see here. You can sketch a large diagram on the next screen to help you understand. I guess I can't sketch here. Then I have a sketch on this one here. Show your thinking here. Well, lattice points there. That's good. We have a lattice point here. So this is 2, and this is, right, opposite the 11-degree angle. That's over here. That's opposite. So our slope ratio here, or what we're going to call it tangent ratio later, we're calling it the opposite over adjacent ratio today. Hopefully you're doing that here, is 2 over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. 2 over 10. Okay, so 2 over 10, right? That is a opposite over adjacent ratio. What can I simplify that to? Well, 1 over 5. That's maybe how you did it. That's maybe how you do that. And they're both valid, okay? What is 1 over 5 written as a decimal? Okay, I type that into a calculator. Do 1 divided by 5. What do I get? I get 0.2. Okay, 0.2. So the ratio is itself, when we get into this into trigonometry, the tangent ratio are all going to be written out as decimals. Ooh, all going to be written out as decimals. This means opposite is 1/5 the size of the adjacent. Let's see here. Who's correct? How do you know? Well, Abdullah's fractions, you want to use a ratio of 5 over 25. What do you think? Hey, is that valid? Hey, we dealt with this on Wednesday. 5 over 25 works because 1 over 5 works. 2 over 10 works. 3 over 15. 4 over 20. 5 over 25. Anything that's in that 1 to 5 ratio works. So who's correct? Abdul is correct. Hamyon is correct too, because 0.2 is equivalent to 1/5, right? That's just the decimal form of the fraction 1/5. And finally, well, Hygen's not right here because we're talking opposite over adjacent ratio. That's something different. Hygen does adjacent over opposite here, it sounds like. So we're not talking 25 over 5, or we're not talking 5 over 1, right? Just 5. So Hygen is incorrect. Abdul, Hamyon, and finally Miguel here. 172 divided by 860. Let's see if that would actually be a similar triangle here. 0.2, there we go. So that is, if we had a right triangle with legs of 172 and 860, opposite the 172 side, got to be an 11-degree angle because that's in a 1/5 ratio. And then the 172 is the one part for every 5 parts is 860. So there we go. I think Miguel is good. Okay, and Miguel are all correct because the ratios they have written are all equivalent to 0.2. They are, right? We can prove that. I kind of talked through it, and that's a great justification if you put that up there. Great, because I wrote it, right? All right, let's keep going here. Time to pause, share ideas, slides 10, 11. To go through both of them, I didn't do the toddler with you guys. I think you'd be able to figure this one out here. Hey, they're over here too. So what are you going to have to do here on this one? 2 feet tall. Well, if we're 2 feet, okay, well, 15 getting to 5, hey, it goes both ways. I can what? I can divide this by 3 to get whatever this is here, the 5. Or what am I doing wrong? The toddler's 2 feet tall. Never mind. How far are the end of the string other than the ground here? Yeah, just multiply by 3. Right, so 6 feet. 1 to 3 ratio. 1 to 3 ratio. 2 to 6 is the same as 5 to 15. They're both in 1 part to 3 part ratios here. Okay, so there's that. As we talk about that here, here's your exit ticket. Maybe I'll stop with this here. I want to see you with your exit ticket here, but I have had questions here. You got to drag this, guys. I'm definitely going to check this to see if you got this here. I got questions here. Somebody asked me what the small triangle was. Small triangle is the blue triangle here, where this is 2.67, and that is 4 for the dimensions here. Again, right angles are right here. We're dealing with the right angle over here all day today. Large triangle, somebody made a very good point, is that there are actually 3 triangles in this diagram. We don't know exactly how long this is. So the large triangle, this one, is we're talking about the green triangle. This is small, and that's large. That's what you're using in the exit ticket, okay? Message me if you have any questions. Hopefully you enjoyed these past few assignments as we're guiding on in here, trying to figure out what we need to look at to tackle these trigonometric ratios, which will start next week. Take care, guys. Hopefully you have a wonderful weekend. Bye.